So we've got to the fifth module of our machine learning series. So if you remember what we did in the previous module, just in case if you've forgotten, it's actually, worthwhile for you to kind of review that, and then before you get, to this fifth module. So in this fifth module, what we're going to look into is, as you can rightly see here, instance-based learning, right? So, but before we look into instance-based learning, there is something which is worth explaining, okay, briefly. So, there's this concept of hypothesis, right? Hypothesis. And from your knowledge of mathematics and statistics, we can actually loosely define hypothesis as what? Any guess? So we loosely define hypothesis as what? Okay, any guess, so you guess. So a kind of, maybe, can we say scientific guess or something? Okay, let's call it a guess that can be provable. That means, if I say, for instance, that all men are smart, right? So can I be able to prove this? Please remember, this is just a loose analogy of hypothesis. So we get to what we call hypothesis testing, or evaluation of hypothesis, or evaluating hypothesis in machine learning. Evaluating hypothesis in machine learning, okay? So after that, we now dive into instance-based learning, okay? So all men are smart is a hypothesis which I have to prove, right? So how do I prove it? So what do you mean by smartness, right? Can we say based on the way they reason or the way they think or the way, but do you think this holds true in all situations? So that leads us to something which we call null hypothesis, hypo, and alternate hypothesis. So null means it's null, right? Okay. Designated as H0, H subset 0, and alternate H subset 1. So simply put, this is the hypothesis that we have to prove or disprove, okay? So this usually has no effect. And then this will always have some effect. So let's use data to answer this question. Because if I say all men are smart, on what notion, on what basis did I actually come up with that, draw that inference, okay, or conclusion? So let's say there is a kind of a test which we call IQ test. IQ test. By the way, IQ stands for intelligence quotients. In this test, so maybe I will administer some test, maybe just do some maybe arithmetic, or maybe give them some test on maybe English speaking test, some English speaking test, okay? And then we get into some logic, and then maybe we look into arithmetic, right? So based on these tests, some scores will be assigned. Now, here is, I need to define the kind of people I'm administering this test to. So, men, fine, let's go to college students. Now in that, say I have just take some sample, and that leads us to two concepts here which we need to understand when we evaluate this hypothesis. Sample versus population. Now, it's not possible for me to administer this test on all the students in a college. Okay, let's make it specific now. All the postgraduate students in a college, right? So if you think of a college, take an example, MITM as an example. Now, all the postgraduate students in MITM forms a population. But do you think this is practically possible for me to administer this test on all the population, right? It's difficult. So I will draw some of them at random, right? Maybe I'll go to the class and pick only the smart guys, right? So I pick a subset of that, subset of population forms my sample, right? So now I will give them this test. Say I took only 10 men, okay? In the IQ test for men, only 10 people were there, right? Now I've given some scores. So English, maybe these poor fellow gods, some value, right? Or some score. Now, if you look at it this way, I don't want to compute each individual score, right? Each individual scores I can take, but I want to check whether this hypothesis holds true, that all men are smart, right? Remember how we started? Smartness, we want to define it in terms of their performance in a prometric test, right? So, and I said, okay, fine, let's use IQ tests, intelligence quotient test. I wrote IG and you didn't find that out. So here, I was like, okay, kind of, let's give in English, logic, and arithmetic. So these three, if it holds true, then I will now reach the conclusion that really men are smarter. And you know for sure, it's not practically possible to administer the test on all men in an entire college. So I drew some stuff, subsets of that, which I call a sample. And in that sample, I computed their individual scores. But what I'm looking for is the aggregate score, right? For me to make draw a conclusion or reach an inference. So what I will do here is, for all the 10 of them, maybe on the average, they scored 83%. Now, for me to prove this right or wrong, so I need to check the other members of the population, right? So now I look at the female population. So the same test, I will administer it on female population. Now again, as you know, we cannot administer the test on all the entire female students in the college. So we drew some samples again from that. And in that, maybe again, 10 samples. Now these samples has to be equally sampled. Okay. So in this now, we got say 84%. Now you do the maths yourself. The men 83% and the female 84%. So what should I do now? What should be the conclusion? You already know, right? So it tells me that, okay, that the female population actually are smarter than their male counterparts, right? So what I do now is, I will get back here, and I will now say, I will now reject the null hypothesis, okay, and accept the alternate hypothesis, okay? I will accept what? H1, alternate hypothesis. Okay, so this is not what we are going to do in machine learning, okay? This is just the basics of hypothesis, okay? So it's a guess that is provable, that is loosely and loose analogy, okay? And then, and here we have taken some example, right? And then we reached at a conclusion that actually women are smarter. Now, this is not a generally accepted way of proving smartness, okay? So the obvious question is, what is a hypothesis? In what? A hypothesis in machine learning. Can you put on your thinking cap and tell me what is it exactly and how do you define it? Can you make an attempt? All right. So if you remember, from whatever we've studied so far in machine learning, we are actually doing what? Trying to come up with a model that will be able to what? Improve its performance on some tasks, right? Based on experience. That was the definition given by Tom Mitchell. Now, if you really want to define hypothesis with reference to the definition of ML, so we say that it is the desire to use available data to learn a function that maps input to output. Okay, you know why I'm speaking slowly? You know, in a couple of videos, people always say that I speak so fast and they are unable to understand. So it might look awkward for me, okay? But please, yeah, try to follow along. Okay, I will repeat again. Getting back to the definition of machine learning by Tom Mitchell, he just defined it, I'm paraphrasing, okay? He defined it, right, as what? a model that will be able to improve its performance at some task with respect to experience. And we've seen lots of cases in that. Now, when we get to hypothesis now, as you know, right? For every machine model, for you to accept whether the machine model has actually learned or not, you need to test it out, right? So that's why in most cases we'll do training, testing, validation. Well, basically we do training and testing. So at training, what you are telling the computer is, this is an input, map it to some set of functions, give me an output. So if you connect the dots, we can now define hypothesis in machine learning, okay, as what? So the ML hypothesis in this refers to mapping a function that best describes the relationship between input and output. All right? So now you got this. Let's get started. So what is the motivation behind evaluating hypothesis? Okay? If you notice, most of the time what you do in machine learning is you always try to compute the accuracy of a model, right or wrong? So I've seen students, they tell, no sir, I designed this program and then, okay, and then I got an accuracy of maybe 80%, right? Then they will tell, no, this is a limitation, sir, because the authors did not, the accuracy did not reach a threshold value. We expected accuracy to be kind of 90%, greater than 90% or 95%, but because it was less than 90%, so the model was kind of wrong. Okay? So to an extent, you are also wrong. The reason being that, see, there are some data sets that are very challenging, okay, for you even to build a proper model in that. And most of these data sets, we encounter them when you work on image data, not on your numeric data. So when you get an image data that is highly noisy, and if you refuse to denoise it, definitely you get an accuracy that might be maybe even around 40% or so. So is your model wrong? No. The only problem was the quality of data which you fed into the model. Another researcher or another student of yours, or your colleague of yours, might also take the same model, but do what we call what? Pre-processing before, okay? Pre-processing. Or try to clean the data, okay? Or clean the data before they apply the model, right? Remember, the quality of your, or the accuracy of your model depends on the quality of data you fed into it. Hence, whenever you look into evaluating hypothesis, okay? Evaluating hypothesis, you are actually trying to understand whether I can actually fine-tune this model to give me a better accuracy, because that's what most of you do, right? To give me a better accuracy or kind of improvise on an existing system, right? Okay? Improvise on the existing model. How accurate is that case? How accurate it is? And you see, this is also a fundamental question in machine learning, right? So I don't know whether many of you still understand how to actually define accuracy. See, we have studied and we've come to reach the last model, okay, of the semester, okay, of our machine learning series, the last model of our machine learning series. But we are actually, if I ask you now, how do you define accuracy? Because this is the big question, right? See, you've seen that when you evaluate model, you are actually trying to do what? Trying to do what? Find the accuracy of that hypothesis or of that model, right? Of that case which you have made. Now, if you remember previously, I said that the initial hypothesis was that all men are smarter. Now, after we prove it wrong, after we prove it based on data, because we believe that data don't lie, now we came to the conclusion that actually women are smarter. Now, we got accuracy of 83 versus 84, right? Now, how do you know that that was actually the correct accuracy? You computed it mathematically, right? And you got 83 and 84. So for us to simplify this further, let me take some, let me keep it like that, 83 for men and 84 for women. Now, that leads me to the question, what is accuracy? What is accuracy? Can you make an attempt, guys? How do you define accuracy? Okay, sir, accuracy is how accurate my model is. I agree. Accuracy is how accurate my model is. I totally agree. But how do you explain that in terms of data now? Because whatever we do in machine learning revolves around what? Data. Because we always say that what? Data don't lie. Now that you have told me that, fine, sir, accuracy is accuracy of the model, and I totally agree to whatever you have said. Now, can you use data and just exemplify? Use data and simplify and tell me. So for us to understand that, let's take an example, okay? Now, I sampled 10 students. Remember, that was how I did that. I sampled 10 students in both cases. Right? Now, for men, so if you look here, 83% accuracy was for men, right? So how about some misclassifications? Because if I want to give a kind of a justification of how accurate my model is, I need to look for what? Misclassifications. Misclassifications. So let me ask you this obvious question. Is this model correct? The answer might be yes and no. Yes, in the sense, yes, I got an accuracy that is greater than a particular threshold. No, in the sense, I need to look into misclassified instances, right? So, in most cases, accuracy doesn't give us the best. We don't evaluate the performance of a model based only on accuracy. Hence, we are going to look into the confusion matrix. Now, as you remember, confusion is what? Are you confused? So are we trying to confuse the model, or are we confused? Or is the model biased? So when we look into confusion matrix, we try to understand, okay, whether there are lots of misclassifications or not. Now, I hope the board is still visible. Now I'm going to take some grids. It's usually better we start with a square matrix. So when I talk of matrix here, I don't know how you pronounce it. I'm talking of this, M-A-T-R-I-X, okay? Not M-E, not M-E. Because M-E is a different thing now. Maybe I'll differentiate between the two. M-A-T-R-I-X versus M-E-T-R-I-X. Fine. Now, here, remember we got an accuracy of 83%, right? Now, follow along. Oh, this might be a little difficult, okay? So I don't want to confuse most of you. So let's take some numbers that are very easy for us to compute, okay? Some figures, 80 versus 85%. Is that fine? So for men, 80, for female, 85, okay? Now, if you see here, 80% might be, remember the accuracy is 80%, right? So let's look for misclassification. So misclassifications will be these two instances. Look there, and this one, right? So anything that revolves around here, they are rightly classified instance. Hence, if you look at this diagonal, this is my true positive, and that is my true negative. See, my emphasis is on true positive and true negative. Now, if you look here, for 80%, and there are 10 of them, right? So I might say 7, 1. Agreed? So what is left? 2 is left. So I can say here 0 and 2. Now, this is one way of representing accuracy of 80%. Let's say when we viewed the, when we visualized the confusion matrix, we saw this. First case. Second case might look like this. And there are n number of possibilities here. I might get here 6 and 2, right? Then I might get here 1 and 1. Or I might even get also 2 and 0, right? Again, if you look here, you get this, right? So if I add this up, what am I saying? I'm saying that accuracy here equal 6 plus 2 upon 1, 6 plus 1, I'm going clockwise now, 6 plus 1 plus 2 plus 1, which is 8 upon 10. Then I usually multiply by 100, which is 80%. Agreed? Now, the obvious question is, how about these misclassified instances, right? So if you see here, this model is very, very different from here. Because if you look at this, we have true positive here, and this is true negative there. True positive here, and the other diagonal is true negative. Fine? Such that true positive plus true negative gives me the correct instances. Now, what is this? This is false positive, and this is false negative. Now, if you remember here now, you see there are lots of false negatives here, right? For false positive, there is none. So I want you to decide in these two models, which one is better. Accuracy is 80%, no doubt. So for you to understand how good the model is, apart from looking at accuracy, we also look at other matrices now. M-E-T-R-I-X. M-E-T-R-I-C-S. Okay, T-R-I-C-S. So these matrices includes obviously we have accuracy. First one, let's start with that. Then you have your precision. Then you have recall. Then you can have F-score. Then you have, which one? Specificity, sensitivity, and all whatnot. Specificity, sensitivity, and everything, okay? Sensitivity, etc. And in between also we try, even when you compute, we check from the classification result also, you might report also, you might even get into micro average, macro average, and weighted average. Micro, macro, and even weighted average. Now, all this is just for you to read up, okay? Because your syllabus revolves mostly on accuracy, okay? Can we simply answer this by looking at both, sorry, I'm blocking the board. Can we simply answer this by looking at both the null and the alternate hypothesis, right? Let's evaluate the what? Accuracy of a hypothesis. It's very easy for you to do it when you have what? More data. Okay? But also is a challenge because in most cases, you might also do what? Overfit the model. In most cases, in some cases also, when you have less data, the model does what? Mugs up the pattern. And again, it might also do what? Overfit. So, what are we saying? There are two possibilities here. But before we solve the problem, we should understand the difficulties that we always encounter when evaluating hypotheses. One is called bias, and the other one is called variance. Okay? So bias in the estimates and what? Variance in the estimates.